move on to section 4. Section 4, radicals and rational exponents. All right. Given a square with a side s, and for submarines it's also called the root of the square. I don't know why. Anyhow, its side or root equals s, its area equals a, then area equals s squared. Okay, that gives the area given s. But suppose we wanted to run it the other way around, given area, find s. Well, we'll say that s is the square root of a. It's a solution to root a squared equals a. Root a is the number which when squared gives you back a. Oh, and by the way, it's the positive solution. I should add that. 2 squared is 4, negative 2 squared is 4, and the square root of 4 is the positive solution too. Okay, here, if we give it various values of s, we get various values of a. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay, that's easy enough. The other way is a little bit harder. A, square root of 0 is 0, square root of 1 is 1. That's good. Square root of 4 is 2. You can see that just by flipping this table, but these are not quite as obvious. Square root of 2, what's that? Well, there's an approximation. 1.414213562. That's to 9 decimal places. Square root of 3 is about 1.732050808, again to 9 decimal places, but it goes on indefinitely. Now, as for square roots, if you have a square of a rational number, then its square root is p over q, also a rational number. That's easy enough. If it's not the square of a rational number, then the square root of a is not a ratio of integers, not what's called a rational number. And if a is less than 0, then it's not on the real number line. The reason why is that when you square any number, it's either positive or 0. So the square root of negative 1 can be neither positive, 0, nor negative. It's off the number line, and it's a different kind of number. We'll get to that later. In general, the square root of a square is an absolute value. Square root of x squared is absolute value of x. The graph of the square root looks like this. Looks like a parabola on its side. It starts out vertical and starts growing ever more slowly. The cube root of x is the number which when cubed is x. In general, the cube of a cube root equals the cube of the cube root of a cube is itself. The graph of the cube root of x is this S-shaped curve, like this. It's defined for negative numbers, and the cube root of a negative is a negative of a cube root. In general, the nth root of x is the number whose nth power is x. If n is odd, then the nth root of x to the n is x. They just cancel. If n is even, the nth root of x to the n is the absolute value of x, and you wind up with trouble with finding nth roots, even roots of negative numbers. We'll define x to fractions this way. A 1/2 power is a square root, a 1/3 power is a cube root, and a 1/nth power is an nth root. So for example, x to the 4/4 is x to the 1/4 power, fourth power of a fourth root, which is just x. Similarly, x to the 2/2 is a square root squared, which is x. X to the 3/3 power is a cube of a cube root, which is x, and so on. So they cancel out as they should. Define x to a ratio m over n is an nth root of x to the nth power, or equivalently, an nth root of an nth power. For example, a 1/2 power is 64. Okay, 64 is 8 squared, and 2 times a half is 1, so you could 8 to the 1, which is 8. 64 to the 1/3 power is a cube root of 4 cubed. 64 is 4 cubed. So these cancel and get a 4. X to the 2/3 power is a little more complicated. It's a cube root of 64 squared. We already have that cube root is 4. So it's 4 squared is 16. X to a 3/2 power is a cube of a square root. We have the square root is 8. So the cube root of cube of a square root is 8 cubed, or 512. Now the rules for exponents mentioned earlier still apply. If you multiply 2 powers of the same base, the exponents add. If you take the ratio of powers to the same base, the exponents subtract. This is even for x and y being fractional. If you have a power of a product, it's a product of powers. Powers distribute. A power of a power is a to a product. Okay. And a negative power is a reciprocal. So, examples. Root 7 times root 28. Well, that's root of 7 times 28, which is root 196, which you can calculate, which your calculator will tell you is 14. Root 48 over root 3, well, that's the root of 48 over 3. That's root 13, which is 4, 16, which is 4. Fourth root of 24 times fourth root of 54, what's that? Well, we'd multiply inside here. That's fourth root of 24 times 54. That's a fourth root of 1296, which comes out to equal exactly 6. Here is a fifth root of a to the 6 times b to the 7th. We'll write a fifth root as a 1/5 power. We'll distribute over the product, a to the 6/5 times b to the 7/5. Now 6/5 is 1 1/5. 7/5 is 1 2/5. So we write that as all this. You get ab times fifth root of ab squared. Here. Root 32 plus root 38. Well, now here we use a trick of simplifying. 32 is 16 times 2, and 16 is a square. 18 is 9 times 2, and 9 is a square. So root 32 is root 16 root 2, which is 4 root 2. Root 18 is root 9 root 2, which is 3 root 2. These are like terms. You can pull out a factor of root 2 and leaving 4 plus 3, which is 7. 7 root 2 is the answer. Here we have a 2/5 power of 32. What's that? Well, 32 is 2 to the 5th. And so here we have a product of a power of a power. We multiply them out. 2 to the power of 5 times 2/5. 5's cancel, leaves 2 squared. That's 4. Here's 4/9 to the negative half. Well, 4/9 is 2/3 squared. Into a negative half, you multiply the powers. 2/3 to the negative 1. That's just the reciprocal, 3/2. 16 over 81 to the 3/4 power. Well, 16 over 81 is 2/3 to the 4th power. That to the 3/4 power means you multiply these exponents. 2/3 to the 4 times 34. 4 times 34, 3/4, excuse me, is 3. So 2/3 cubed, which is 8 over 27. And here we have a thing called rationalizing the denominator. The problem being is that squares can be such a pain in the neck. And dividing is also a pain in the neck. And both together is just unsupportable. So what we do is manipulate these in a way that makes the square roots disappear from the denominator. That's called rationalizing the denominator. And we'll do that by multiplying above and below by the same square root, so it will cancel. 1 over root 6, you multiply above and below by root 6 over root 6. 1 times root 6 is root 6. Root 6 times root 6 is 6. And there it is, root 6 divided by 6. 3 over root 2, similar thing, we'll multiply above and below by root 2. Root 2 times root 2 is 2, and the numerator is 3 root 2. So you get 3 root 2 divided by 2. 9 over root 3, what's that? Well, multiply above and below by root 3, and the numerator is 9 root 3. The denominator root 3 times root 3 is 3. 9/3 cancels, leaving a 3 root 3. So there's more rationalizing the denominator. Here's a 1 over cube root, which is 1 over x to the 3rd. Multiply above and below by x to the 2/3. This way, x to the 1/3, x to the 1/3 plus 2/3 is x to the 1, which is x. This will be x to the 2/3. So x to the 2/3 divided by x. So a cube root of x squared, all that divided by x. 1 over 6th root of x to the 5th, that's 1 over x to the 5/6. Multiply above and below by x to the 1/6. In the denominator, x to the power of 5/6 plus 1/6 is x to the 1, which is x. Underneath x to the 1/6. So you get 6th root of x, that divided by x. Here's 1 over the 7th root of x to the 3rd. So in other words, 1 over x to the 3/7. All right, we'll multiply above and below by x to the 4/7. And why 4/7? Because 3/7 plus 4/7 equals 1, x to the 1. Underneath x to the 4/7, so this is 7th root of x to the 4th, all that divided by x. Okay.